Nalini Sooknanan Pillay. She's graduated with an engineering degree at the University of Witwatersrand in 1994. I shouldn't have said that. She worked as a production engineer in the steelmaking industry, where she dealt with expansion and optimization projects. In 1997, she joined Eskom's research business unit, where she was involved in generation plant-related research, as well as the development of knowledge management diagnostic programs. At the end of 2011, she set up the Eskom System Dynamics Center while completing a Master in Sustainable Energy Engineering at UCT. That was also, I think, the year of our first conference, was it 2012? So yeah, thereafter, after a master's, Nalini completed a PhD in industrial engineering with contributions to the field of systems engineering at Stellenbosch. She currently holds the executive role of Eskom Corporate Specialist in System Dynamics, and she's a founding member of the South African System Dynamics Society chapter, and she held the post of president for a few years, and still lectures applied system dynamics at various universities, and has authored and co-authored internationally recognized papers and a book or two. What she doesn't put in her bio, but I know, is she also writes children's books or young adult books. So Nalini, without further ado, please talk to us about electric vehicles, a tailpipe dream, or should that be a sewer? I mean, a outlet pipe. Thank you, Nalini.
Okay, thanks, Andries. Just going to put this off. Let me reduce this and view full screen. All right, am I audible and visible?
Audible and clear. Audible and.
All right, okay, great. So I just want this. So good morning again, everyone. This time, I'm going to present to you on a research study that was conducted about a year back, actually, with data that's still being updated and validation that's still ongoing. The results that I would like to share with you is on the emission side of electric vehicles when compared to your internal combustion engine vehicles. So now we know that the South African greenhouse gas inventory indicates that the energy used in the transport sector actually contributed to approximately 8.4% of South Africa's greenhouse gas emissions. Of that, road transport actually accounted for about 75% of the transport emissions. Now, in light of this, the country pledged to introduce mitigation methods or efforts to reduce the emissions as per the 2015 Paris Agreement. Part of these measures and efforts was to develop the green transport strategy that was drafted to include a series of strategies that would support efforts to reduce your greenhouse gas emissions. The South African Minister of Industrial Affairs had signed a pledge to support this Paris Agreement on climate change commitments that was already in April 2016. And then we were looking at average emissions reductions of about 95 grams of CO2 per kilometer for all new cars by year 2021. This means that our fuel efficiency should have been something in order of about 4.1 liters per 100 kilometers of fuel for your petrol vehicle, or 3.6 liters per 100 kilometers for your diesel vehicle. That, just as a matter of interest, would have been a 27% improvement in your fuel efficiency from 2015 to 2021. But besides these fuel efficiency improvements, your electric mobility solutions that were being looked at included replacing your internal combustion engine vehicles, your ICEVs, with your electric vehicles, your EVs, as an effective way to actually reduce your carbon emissions in the transport sector. So here in this study, I use system dynamics as a modeling methodology, developed a simulator to try and understand, are we really getting the right numbers when it comes to our carbon emissions in the transport sector. When we look at our different drivetrains, compare your ICEVs to your battery EVs, your BEVs, to your hybrid EVs, your HEVs, to your plug-in hybrid EVs, which is your PHEVs, and your hydrogen-fueled EVs or fuel cell EVs. Now, here we looked at your tank-to-wheel emissions, and we looked at well-to-wheel emissions. Now, well-to-wheel emissions are not the same thing as your life cycle analysis. If you're looking at a life cycle analysis for a vehicle, you would look at the fuel supply cycle, which includes things like your resource extraction, to produce the fuel tank, your vehicle cycle, which would include things like your vehicle manufacture, running costs, disposal, or recycling, and so on. And you would possibly look at your infrastructure cycles, besides looking at battery production and so on for these vehicles. This study did not consider all of that. It just looked at your well-to-wheel in the sense of those emissions related to your fuel production, processing, distribution, and of course your use. Now, in terms of the system dynamics methodology that was used and is being used in Eskom in the System Dynamics Center, when we first get a problem, we do help the customers try and contextualize the concept that they have. In supporting the customer to contextualize the project requirements, what we do is we ask them, like, what do you think should be the graphical outputs or the variables that you want to understand when you run the model? Now, we're not telling them, listen, what answer do you want to see? We're actually not at all prescribing a preconceived result in terms of the emergent model solution. Because the resultant trend or the graphical result, it is of course non-intuitive. It is non-intuitive and unexpected, but it does allow the customer to reflect on the system variables which may have to be reported on, and then it helps us to establish a firm focusing question. When it comes to the boundary setting step of it, we develop the causal loop diagrams or the system architecture maps through processes such as your group model building. We have facilitated participatory modeling methods where we would guide our stakeholders through a brainstorming session to determine the variables, relationships between these variables, and so on. And then we would go on to the system analysis. Now, the system analysis is a very, very important step, and it is, in my opinion, far more important than the software, the model. This is where you actually have to understand your data. You have to, order and simplify both your qualitative and quantitative data into the time resolution that would be suitable for the model. And if you do not do that, you actually don't understand your data. You don't understand when things go wrong in your model. And the analysis can include a variety of methods. It could be statistical methods. It could be programmable codes, any number of things. The next step then is to develop the model. When we do develop the model, in our case, we use IC Stellar Architect as the software. And we then determine time resolution from what year until what year are we looking at. If there's any historical information, we then require that as well. We then define our parameters and we parameterize our variables with numbers that are obviously, in most cases, empirical. We do then have a step that we call validation and policy insights. This is where we start running scenarios. But the validation step is actually not only at this point. We do validation throughout the project lifecycle. The model is then generally handed over to a customer to be able to run their scenarios and further understand and interrogate the model and the results. And then in some cases with the very long-term models, we do step in every now and again, maintain the model in terms of data updates or even minor structural changes. The analysis for this particular project, this was a preliminary analysis. In this case, data was obtained from the actual number of EVs in the country from year 2015 up until year 2021. And looking at the empirical historical EV sales in South Africa, the hybrid EV seem to be the most popular, with sales being almost 3 times more than your full battery EVs in year 2021. This dominance, of your hybrid compared to your plug-in hybrid and your full battery is very comparable to the distribution that we have in the United States. Part of this analysis was then understanding, okay, the relative difference between the drivetrain sales. And then we did regression analysis to determine the possible number of EVs in 2040. The target that we then determined for 2040 would then be fed into the logistic equation that was then structured in the model to then run and determine what the impact would be for that particular target on your emissions. In this particular analysis as well, we did linear regression analysis. We did lots of transformations. Lots of higher order regression analysis showed that the R-squared, or the goodness of fit measure, or the coefficient of determination for the regression models is actually really high for a lot of the higher order equations. So like a lot of them were like over 99% your R-squared. And then the question is like, which one do you actually choose? Now that's very important, because you actually then have to understand the data you're working with, understand the environment in terms of where the EV sales, what's actually happening, to be able to, in the EV environment, to be able to then select the correct equation. It's not just about looking at that R-squared value. So that's some of it there. So after the analysis, the values, the targets that I used in the simulation was then 188 or 189,000 of your full battery, 457,000 of your hybrid, and about 15,000 of your plug-in hybrids. Obviously, you can't just feed in EVs, because each one of these have different battery configurations. And so these then were the targets at the time of writing the report. Subsequent to that, we received more information, more data on the EV sales from Uyilo, that's Hiten Parma specifically, and that then changed the trend significantly in terms of what the 2040 target value could potentially be. But I have worked with these values, and so the results I shall present to you would be based on these targets. Here we have the model structure. Like I said, we use IC Stellar Architect as our system dynamics modeling software. We develop a lot of sub-modules and modules. We identify state variables, and we initialize our stocks with various conditions in terms of values. And of course, we establish the mathematical linkages of variables. This particular one has no feedback, but there are stock flow feedback structures in the model. Here I just showed you what it typically looks like. These square blocks are your stocks. These are your inflows and outflows, and a whole lot of other variables. In this particular case, this is just showing us a part of the generation module that built-in battery storage for a new PV that would come into the system. The user can then define these things. So besides this, that also impacts your generation mix, which then also impacts your calculations for your well-to-wheel emissions. It was important to then ensure that we had a very detailed generation module. This is just generally, this is then what the results look like from running the generation model in the simulation. We did build in the IRP 2019 future options. I did build in the decommissioning plan, which we got from our operational guys. And some of the future ones would be decommissioned automatically depending on what the user did select. So you can disable the IRP options and put in your own user defined options and see what the mix would be like. And of course, depending on what the mix is, you have very, very, very different values in terms of your grams per CO2 per kilowatt hour for your different types of electric vehicles. You'll see the difference between, say, Iceland's, which is more renewable, compared to South Africa, which is far more coal heavy. So that's why this part of the model was important. Then in terms of the results, I ran a base case scenario with without EVs. This is for my ICEVs. So this is just looking at the cumulative emissions up until 2040. And this was just for our ICEVs tank to wheel. What I then did was I introduced EVs, and then I calculated my tank to wheel, and you find that there is definitely a reduction in terms of your carbon emissions. So this is what everyone looks like, and they're like, all systems go, this is fantastic. We definitely need the EVs. However, if you then look at your well-to-wheel emissions with the same target number of EVs, you find there's actually far more carbon emissions that's been generated than what we perceive. And yeah, and I think these are things that we have to be aware of. So here we might have like a 10% decrease from our baseline, but here we have something like a 16% increase if we look at your well-to-wheel emissions. Here, these are for the different drivetrains. Again, you'll see that there's quite a difference in terms of your tank to wheel and your well to tank and your well to wheel emissions for all of your electric vehicles. Clearly, far more. I mean, for your full battery, for example. I mean, if we look at full battery, we think that our tailpipe emissions are zero, so it must be a fantastic option in the transport sector. But if you consider your well-to-tank emissions, you actually do have a significantly higher carbon emissions than even your hybrid. Here we then have a comparison of all of the different drivetrains, and here is where I then introduced your fuel cell EVs. Now I did not use the fuel cell EVs EV as an option in my other scenarios because we don't have any. Toyota or Andres is going to try and see if Toyota can get their Mirais in at least. Hopefully soon, and then perhaps we can get some empirical data from running those vehicles as well. However, in this particular scenario, I just put in 100,000 vehicles of each of these electric vehicle categories over a annual distance of about 10,000 kilometers, just to see what the relative impact would be. And if you look at this relative impact, what you find is that if you actually, if you produce hydrogen, this is gray hydrogen using fossil sources, compared to if you use renewable sources to generate hydrogen, there's a significant difference in terms of the carbon emissions. And clearly, unless you're going renewable with your hydrogen vehicles in terms of generating your hydrogen, it's not a suitable option. here what you also find is that your battery EVs are certainly more than your hybrid, but far less than your plug-in hybrid in terms of your well to tank emissions. In conclusion, I would like to say that the system dynamics, I mean, it's a loved and wonderful method. We've used it since 2010 in Eskom. And it proved to be a very valuable and effective modeling tool. A lot of these results have fed into results that were shared with EXCO as well as Eskom's board in terms of planning for our fleet replacement of our ICE vehicles with EVs. So you know, I think we're all aware that our electricity mix is very coal heavy. So, you know, getting to better carbon emission values would also mean that we'd have to relook at this. We certainly need a higher renewable mix in our generation technologies. And of course, like I explained, your hydrogen fuel vehicles are perceived as being as beneficial of your battery EVs. Everyone says, listen, these vehicles are zero tailpipe emissions. But yes, if you look at the bigger picture, your well-to-wheel emissions, it's a different story. It is also recommended that, you know, future work did have to be carried out. We should look at your life cycle costs, not just the well-to-wheel emissions linked to the EVs. However, that might be a lifetime project because I think it would be quite huge. So that's it from me. Thank you.
Thank you, Nalini. We have time for one question. One comment, Marisa in the country, they are just we're trying to get the paperwork sorted to transport them from the Durban port to Johannesburg. Not an easy feat because there's no regulations for hydrogen in South Africa. So if anybody's got an idea on the regulations, please let us know. We're very interested. Thank you very much, Nalini. I think very insightful. And as you say, this is something that we're going to have to deal with for quite a while. Question I would do want to ask you is, were you looking just from a demand side in terms of vehicle sales, or you were looking from a supply side?
It's a demand side for sure.
Okay,
maybe
thank you.
We could supply as much as we can and want to supply, but it is then the uptake which is far more important.
Unfortunately, the constraint is supply and not demand.
Not just
because nobody trusts us. Nobody trusts us with hydrogen.
Yeah.
So I'm in the motor industry. I'm very familiar with these problems. So thank you very much, Nalini. Our next speaker is Ashok.
Sorry. Can I just answer the one question by Rem? He says that what are the ways for validation of a model other than historical data? So if you don't have historical data, they have, you know, the one way is actually sitting with subject matter experts who know a lot about the industry and creating your own proxies so that it makes sense. The other thing you could do is look at academic information, and as well, I mean, test your mathematical structures as well to make sure that, you know, it is validated mathematically in terms of the model, structurally, in terms of the behavior of the model, but also in terms of the data and the results. And yeah, like I said, it can be validated through those ways as well. Yeah, thank you.
Thank you.